In this video, I'm going to show you how spontaneous symmetry breaking works in quantum electroweak theory, also called the Weinberg-Salam Model. Note that quantum electroweak theory is a rather complicated topic, and I'm not going to introduce the entire subject in this video. This isn't some kind of general introduction. The goal of understanding how spontaneous symmetry breaking works in QEW is a rather specific goal. Because the point of this video is just to learn how spontaneous symmetry breaking works in QEW, I'll not even write out the complete three-generation theory. I'll save that for a future video. In this video, I'll attempt to keep the math as clear and simple as possible by restricting the theory to the simplest set of particles that can fully demonstrate this part of QEW. Not only will I include only one generation, but I'll also only include leptons. This is actually all that's needed to see how spontaneous symmetry breaking works in QEW. Adding the rest of the fermions, which I'll do in a future video, changes very little in the unbroken and spontaneously broken Lagrangian densities. In that future video, I will simply generalize the results obtained here to the case of more fermions with simple modifications. This is actually the easiest way to handle the whole theory anyway. So ultimately, the specific goal of this video is to write out and understand the unbroken QEW Lagrangian density for one generation of leptons, and then compute the spontaneously broken QEW Lagrangian density from it. Let's get started. Throughout what follows, when I say the word direct between two group names, like SU2 direct U1, I'm referring to the direct product of those two groups. Quantum electroweak theory is based off of the premise that everyday electromagnetic and weak interactions result from the spontaneous symmetry breaking of a particular minimal SU2 direct U1 gauge theory. Such a premise originates from the need for a renormalizable theory with massive vector bosons in it. The spontaneous symmetry breaking of a massless vector gauge theory being the only known way to achieve this. This renormalizability issue will be discussed further in future videos. The specific Lagrangian for QEW was selected based on what form it needed to have in order for spontaneous symmetry breaking to yield a low-energy Lagrangian density that's phenomenologically correct. For one generation of leptons, the specific Lagrangian density that happens to do this is this, the so-called Glashow-Weinberg-Salam model for one generation of leptons. Let's go through what's in this Lagrangian density. The gauge Lagrangian density consists of the usual SU2 and U1 gauge field Lagrangian densities. The lepton dynamical Lagrangian density, or fermion kinetic term as I'll regularly refer to it throughout this video, consists of three Weyl massless fermion Lagrangian densities. One for the left-handed neutrino, one for the left-handed electron, and one for the right-handed electron, all with covariant derivatives to make them gauge invariant. The Higgs Lagrangian density describes a Higgs field isovector doublet that transforms into fundamental representations of both SU2 and U1, as is made clear by the form of the gauge covariant derivatives that render its kinetic term gauge invariant. Beyond the kinetic term, it consists of the famous Higgs potential, which induces spontaneous symmetry breaking in the first place, and finally a strange-looking Yukawa coupling, which is designed to give mass only to the electron and not the neutrino. It's worth considering for a moment how the Yukawa coupling term actually accomplishes gauge invariance. From the gauge covariant derivatives, we can see that the fermions and the Higgs boson must transform according to these gauge transformation laws. We can see that U1 gauge invariance in the Yukawa term is produced in kind of a cool way. U1 factors coming from the left-handed electron and the Higgs field are both required to cancel the U1 factor coming from the right-handed electron. SU2 invariance also comes about in a cool way. The left-handed electron and neutrino form an SU2 isovector doublet just like the Higgs. The SU2 factor from the left-handed lepton doublet cancels against the one from the Higgs doublet. From this, you can see that the specific fractions multiplying the coupling constants in the covariant derivatives are one possible selection for producing a gauge-invariant Yukawa coupling. This particular option is selected because it ends up uniquely giving the correct electric charge assignments in the spontaneously broken theory. You'll see how this works shortly. Speaking more generally, it might seem like a very difficult thing to guess that this complicated Lagrangian would happen to spontaneously break down to what correctly describes low-energy phenomenology. However, at least these days, the task of justifying it isn't as difficult as you might think, because we have a lot of experimental data and know that spontaneously broken gauge theories retain renormalizability. The task basically reduces to writing down gauge theories with the right fermions in it and the right number of vector bosons, starting with the simplest options first, and then calculating the spontaneously broken Lagrangian densities until you find one that matches your detailed experimental data. This is a short task because SU2 direct U1 is one of only a small number of minimal options, which you would naturally try first, and it turns out to be correct. One could, of course, start with theories that contain a larger number of gauge bosons than required, supporting a higher symmetry, and then break them in multiple stages with multiple Higgs multiplets. But this isn't the simplest option and would necessarily just reduce to the correct simplest option at the energies we're currently able to probe. However, while we ignore these possibilities for a basic theory of weak interactions in electromagnetism, the idea of embedding the full standard model with SU3 direct SU2 direct U1 symmetry in a more symmetric theory is the subject of grand unified theory. It's important to note that this is only how we motivate/justify the Lagrangian today. Historically, the process was much harder. When the theory was first written down by Weinberg in 1967 and Salam in 1968, it hadn't even been proven that such spontaneously broken theories were renormalizable, and physicists certainly didn't have the fancy LHC and other data that we use to justify the selection today. They based their guesses on different and less convincing grounds. Then, in 1971, 't Hooft proved that such theories are renormalizable. Many competing theories could then be ruled out based on the data that was already available, followed by better data which further verified specifically the Glashow-Weinberg-Salam model as the correct Lagrangian for QEW. Highlights include the discovery of the W and Z bosons at CERN in 1983 and the discovery of the Higgs boson at CERN in 2012. Anyway, with the unbroken ElectroWeak Lagrangian density explained, we're left with the task of actually calculating the spontaneously broken Lagrangian density. We have the usual situation of a Higgs potential that causes the Higgs field to develop a non-zero vacuum expectation value at low energy. We must therefore expand around a new physical vacuum, the standard selection being this. We see that three fields have been set equal to zero in the vacuum. Goldstone's theorem therefore leads us to expect three broken generators and three massive vector fields in the spontaneously broken Lagrangian density. Also, given that there are only four generators in an SU2 direct U1 theory, we expect only one gauge symmetry to survive the spontaneous symmetry breaking process. We'll come back to these predictions as we proceed through the calculation and are able to verify them, which will mostly be at the end when we have the final spontaneously broken theory in hand. By now I've shown you enough of these problems that you likely know that we insert this field reparameterization into the original Lagrangian to calculate the spontaneously broken Lagrangian, rendering the intermediate steps a mere formality. The intermediate steps being finding all the generators that annihilate the vacuum, writing out the full scalar field reparameterization including the Nambu-Goldstone bosons, and writing out the gauge transformation that absorbs the Nambu-Goldstone bosons into the vector fields. In this case, the last two steps are still just a formality, and I'll ignore them in this problem. The first step, however, yields information that we definitely need, given just how differently this calculation will play out compared to the examples that I've shown you already. So let us commence with step 1. The generators in this theory are these. We notice immediately that the set of generators that annihilate the vacuum does not include any single one of these. Look carefully and you'll see that the only generator that annihilates the vacuum is this. This confirms the last of our predictions from Goldstone's theorem, namely that only one gauge symmetry survives spontaneous symmetry breaking. Q taken alone obviously generates U1, but a different U1 than is associated with weak hypercharge. I'll call it U1EM because it must be the U1 symmetry associated with electromagnetism, given that we're taking this theory to be ElectroWeak theory. When we're finished with the calculation, we'll find that the U1EM portion of the spontaneously broken Lagrangian density does in fact match electrodynamics. Also, I've already established that this is the correct ElectroWeak theory anyway, so I mean, it's not exactly ambiguous. Anyway, as a result of this identification, I'll use the phrase Q charge and electric charge interchangeably throughout. I'll also do this with other associated phrases. The fact that the unbroken generator is a non-trivial linear combination of the original generators is the key realization that makes step 1 particularly particularly necessary in the case of this problem. Specifically, the fact that the unbroken charge is a linear combination of generators rather than a set of individual ones will complicate the reparameterization. We know that the physical spectrum of the low-energy theory must be a set of particles that are both mass eigenstates and eigenstates of any conserved charge. However, since the only conserved charge is a non-trivial linear combination of the original generators, the low-energy charge and mass eigenstates will be a different basis than the high-energy SU2 direct U1 charge eigenstates, at least partly. Therefore, reparametrizing the high-energy theory to obtain the correct low-energy one will be more complicated than just inserting the gauge-transformed Higgs field reparameterization. It will also involve a change of basis to the low-energy spectrum of states. Another way of saying that is that we also need to change to the physical at low energy vector field basis. The systematic way to figure out how to reparameterize the theory to reveal the correct low energy Lagrangian density is to look at how all the fields transform under the transformations generated by Q and how they couple to the Higgs field. From this, we can identify which combinations of them will correspond to mass eigenstates and Q eigenstates. To be clear, by correspond to mass eigenstates and Q eigenstates, I mean that their field quanta are mass and Q eigenstates. This is where we begin to see how the specific fractions multiplying the coupling constants and the covariant derivatives yield the correct charge assignments, as I was saying a moment ago. For the fermions in the low-energy Higgs field, this process is easy, but for the gauge fields, it's a lot harder. The easiest approach I can think of is to start by doing this for the easy particles and then begin reparameterizing based on that. As we go, we can identify within the Lagrangian density which linear combinations of gauge fields apparently correspond to mass and Q charge eigenstates. We can then use this information to reparameterize the rest of the Lagrangian density, at least the parts of it that depend on vector bosons. Let's get going with this. For fermions in the low-energy Higgs field, I said that it's easy to identify which combinations of fields correspond to simultaneous mass and Q charge eigenstates, and that's because the individual fields themselves correspond to mass and charge eigenstates in the low-energy theory. We can see from the Yukawa coupling term that the electron and neutrino will correspond to mass eigenstates. The Higgs potential makes it clear that the low-energy Higgs field will also correspond to a set of mass eigenstates, where I use the plural because of multiparticle states. The gauge transformation laws make it clear that the electron field has charge -1 under Q, and the neutrino a charge of 0. They also show that phi 0, and by extension the low-energy Higgs field, correspond to Q eigenstates of charge 0. As it happens, the gauge transformation laws for the high-energy Higgs field also show that phi plus has a charge of 1 under Q, but this isn't as important because it doesn't show up in the low-energy theory. With this information, we can start reparameterizing the theory in an effort to identify which linear combinations of gauge fields simultaneously correspond to mass and charge eigenstates. Given that we understand the fermions in the Higgs field already, the logical place to start would be either the Higgs or the fermionic kinetic term. If I didn't know what I was doing, I would just pick one of them and then select the other if my first guess didn't work out. However, I know from experience where to find what I'm looking for, and it begins with a very specific piece of the fermionic kinetic term that will reveal what charge eigenstates result from the W1 and W2 fields. Towards this end, it's necessary to expand out and then break up the fermion kinetic term in the following manner. First, inserting the gauge covariant derivatives produces this. We can then expand out the A-index sum and reorganize it, and then we can break it up to useful effect like this. The piece that will help us understand W1 and W2 is R. If we expand R out completely and insert the Pauli matrices, we're able to conveniently pull out the fermionic factors. We see that we have fermionic factors including a neutrino field and an electron field coupled to a complex vector field. By looking at the gauge covariant derivatives, we've already identified the associated charges/gauge transformations of the electron and neutrino fields. Using this knowledge, we see that for this term to be gauge invariant under the transformations generated by Q, which we know holds, W1 minus IW2 and W1 plus IW2 would have to transform under Q gauge transformations such that their field quanta are charge eigenstates with charges +1 and -1 respectively. The usual notation for this pair of linear combinations is this. where the factor of 1 over root 2 is just a conventional normalization. If you haven't guessed, these are the iconic W plus and minus boson fields. With this notation, R takes on this form. We can then use standard identities to re-express this in terms of Dirac spinors. This is useful partly because the electron field will be acquiring a mass in the low-energy theory, but also because it helps us identify currents later on. Regardless, using standard identities, we have these equalities. This means that R takes on this form, where LC, with C standing for charged current, is the conventional name for this part of the spontaneously broken Lagrangian density. With these results, we've solved part of the puzzle. We've identified the contributions of W1 and W2 to the low-energy charge spectrum, but we haven't yet proved that these linear combinations correspond to mass eigenstates, and we haven't figured out W3 and B yet. At this point, it's actually useful to take a close look at the Higgs kinetic term. This will give us information on the low-energy vector mass spectrum and actually the charge spectrum as well. We'll have a chance to verify that the W plus and minus fields correspond to mass eigenstates, and it will also inform us on what contributions W3 and B make to the mass spectrum. Additionally, it'll tell us one part of their contribution to the electric charge spectrum and suggest a form for the other part. With that information in hand, we can examine a different part of the fermionic kinetic term to confirm that suggestion. With that, we'll have completely solved the puzzle of how the vector bosons manifest at low energy. Another way of saying that is that we will have figured out how they contribute to the low energy spectrum of the theory. Still another way of saying that is that we will have figured out the physically correct vector field reparameterization. We will therefore have what we need to finish reparameterizing the whole Lagrangian density to obtain the spontaneously broken / low energy theory. This may seem like a long process that would take some experimentation to figure out, but I still think it's the easiest way to find the low-energy theory. Anyway, on to the Higgs kinetic term. To remind you, the Higgs kinetic term, the required gauge covariant derivatives, and the gauge transformed scalar field reparameterization are these. Inserting everything into the Higgs kinetic term yields this, expanding the I-index sums, simplifying, expanding out the A and B sums, inserting the Pauli matrix component values, and distributing the overall factor of a half ultimately reveals the presence of the W plus and minus fields in the spontaneously broken Higgs kinetic term. Inserting them in and distributing the V plus H factors gives us this. We are then free to refactor the entire last term. Next, we can see that the first of the refactored terms vanishes completely due to internal cancellations, leaving us with this. We can then internally refactor the second term and then reorganize the squares such that all the vector boson mass terms are clearly visible. Looking at the highlighted terms, we can both verify that the W plus and minus fields do correspond to mass eigenstates as we were hoping, and we can also see what contributions W3 and B give to the mass spectrum. Specifically, we have that GW3 minus G' correspond to a set of mass eigenstates, again plural because of multiparticle states. And we have that the other contribution that W3 and B make to the spectrum of the theory is a massless particle because there are no more vector boson mass terms showing up in the spontaneously broken Higgs kinetic term. The conventional notation for GW3 minus G' is this, where I have made this weak mixing angle definition. We can also define masses. Plugging all of this in gives us this result for the spontaneously broken Higgs kinetic term, where LHV is the conventional name for this portion of the spontaneously broken Lagrangian density. As you may have guessed, Z mu is the field corresponding to the famous Z boson. There are a few other things to notice about it. First of all, it's a real field. It therefore can't carry electric charge and must contribute a neutral particle to the charge spectrum. Also, when the Z boson is written in terms of the weak mixing angle, it appears to be the result of a rotation performed on the original W3 and B fields. Given this apparent rotation, one might suspect that the missing massless vector field would simply be the other part of that rotation, specifically this. Whatever the form of the missing vector field is, we know that it's the only massless vector field in the theory. It therefore must be the one that supports electromagnetic gauge invariance. Therefore, all that remains to be seen is that the electromagnetic current really does couple to a vector field of exactly the form of A mu. If it does, then it's the field we're looking for. Also, note that A mu is a real field and would therefore contribute a charge zero particle / set of eigenstates to the electromagnetic charge spectrum of the low energy theory, which is also consistent with our understanding of U1 gauge theory and electrodynamics. The confirmation that A mu does couple correctly to the electromagnetic current comes from the S part of the fermionic kinetic term. The approach I'm going to take is to assume that A mu is the missing vector field and re-express S in terms of it and Z mu. We will then be able to see that it does in fact couple to the electromagnetic current correctly. The inverted relations that we need for the substitution are these. Inserting them, expanding out the weak isospin indices, and inserting the Pauli matrix components leaves us with this. We can then rewrite all of this in terms of Dirac spinors. Using standard identities, we find these expressions. Substituting these into S leaves us with this. We can then factor and simplify the last two terms. I said earlier that it was useful to write everything in terms of Dirac fermions, partly to make familiar currents easier to identify later on. Looking at our latest expression for S, we see these two currents showing up. Inserting these leaves us with this, and some refactoring gets us here. This can be simplified further using identities derived from the definition of the weak mixing angle and this elementary electric charge definition. Inserting all of these gives us our final result for the S quantity, where Ln, with n standing for neutral current, is the conventional name for this part of the spontaneously broken Lagrangian density. One can see that A mu does in fact couple to the electromagnetic current such that it must be the missing low-energy vector field. We've therefore completed the discovery and verification of these vector field reparameterization equations, which give the correct vector boson spectrum of the theory at low energy. We're therefore free to reparameterize the rest of the theory and thus obtain the complete spontaneously broken or low-energy Lagrangian density. Let's continue by finishing the fermion kinetic term. We only have one bit left. To finish recasting the fermion kinetic term, all we have to do is rewrite the electron part of T in terms of a Dirac spinor. Expanding out the left-hand part gets us here. Combining the electron parts then leaves us with the desired final result. I left the neutrino kinetic term written in terms of Weyl spinors here because it's more compact that way. The neutrino doesn't gain mass through spontaneous symmetry breaking, and unlike with the other parts of the Lagrangian, there are no currents to identify here. With this, we have all we need to write out the complete spontaneously broken version of the original fermionic kinetic term. Specifically, adding our results for R, S, and T together gives us this. With the fermionic term completed, it's probably worth finishing the only other part that we've gotten a start on but not finished, and that's the Higgs sector. We already computed the spontaneously broken Higgs kinetic term as part of our effort to understand the low-energy manifestations of the original gauge fields. This leaves us with the potential term and the Yukawa coupling term to sort out, then we can move on to the gauge term. Let's work on the Higgs potential first. The first step is to insert the gauge-transformed scalar field reparameterization. The next step to obtaining the canonical result is refactoring this by power and h, which gets us here. Constant terms don't matter in the Lagrangian density and can be ignored, so that simplifies it down a little bit. Inserting the previously given value of v causes the linear term to vanish and the quadratic term to simplify, getting us here. If we make this low-energy Higgs mass definition and apply a few definitions given previously, we obtain the canonical expression, where LH is the standard label for this portion of the spontaneously broken Lagrangian density. Now that the Higgs potential term is finished, let's handle the Yukawa term. The first step is to insert the gauge-transformed scalar field reparameterization. Next, we must factor. Then we can rewrite it in terms of Dirac spinors and then define an electron mass and apply the formula we already had for the W boson masses to get this, where Ly is the standard notation for the low-energy Yukawa coupling. We now have all we need to write out the complete spontaneously broken Higgs sector Lagrangian density. With the Higgs sector complete, all we have to do to finish the entire problem is reparameterize the gauge sector of the theory. Unfortunately, this is the most arduous part of the calculation. Because the gauge Lagrangian density depends only on the vector fields, computing its spontaneously broken form amounts to changing basis on the vector fields using the reparameterization that we already uncovered. I think the easiest way to go about this calculation is to invert the reparameterization and then substitute those values into the existing Lagrangian density. To remind you, the vector field reparameterization is given by this set of equations. Inverting these relations provides us with these substitutions. The task of substituting these in is conceptually trivial but quite long. It turns out to be a good strategy to expand out the gauge Lagrangian density and then break it into pieces that can be handled more easily. We can then perform the reparameterization on those pieces separately and then combine them together at the end. Remembering these formulas for the field strength tensors, we can see that the expanded gauge Lagrangian density takes on this form. One could break this up in a myriad of different ways and get a handleable calculation that yields the correct answer, but prior experience working through this problem tells me that the most convenient way to break it up is specifically this. This way of breaking up the Lagrangian density happens to group terms such that each piece corresponds to a compact component of the final answer. This facilitates early simplification, making the calculation a little easier. Let's get started reparameterizing all of these pieces. We'll start the calculation with V1. We see that it can be simplified even before making the substitution. Inserting the value of W3 expressed in terms of the new vector fields yields this. Multiplying this out gets us here. We can then conveniently refactor to get this. This can be simplified even further to yield our final result for V1 by recognizing the appearance of the electromagnetic field strength tensor and the analogous Z field tensor. Inserting these gets us here. Now for V2. The preliminary simplification works just like with V1. Inserting the value of B expressed in terms of the new vector fields produces this. We can then multiply this out and simplify. Next, we can make the same F mu nu and Z mu nu substitutions that we did in V1 to obtain the final result for V2. Finally, adding V2 to V1 gives V. Initially, we get this mess, but upon reorganization, we see that it simplifies massively. Not only does the Pythagorean trig identity simplify the rank 2 tensor terms considerably, but the entire rest of V cancels out, leaving us with this final result. With V done, let's move on to W1. W1 can be simplified down before substitution in the same way as with the terms in V. Inserting the value of W1 expressed in terms of the new vector fields yields this. Multiplying this out gets us here. This can then be factored to reveal W boson analogs of the electromagnetic field tensor, which are labeled as follows. Inserting these gives us this final answer for W1. Naturally, we're going to do W2 next. The same familiar initial simplification happens here too. Inserting the value of W2 expressed in terms of the new vector fields yields this. We can then multiply out and refactor to reveal the presence of the W field tensors. Substituting them in gives us this final answer for W2. With W1 and W2 finished, we can compute W by summing them. This can be simplified considerably. The first step is to multiply it all out. The highlighted terms then cancel. It's also useful to reorder the remaining terms to prepare it for the next step. If we then do some index flipping and relabeling based on the fact that W minus mu nu and W plus mu nu are antisymmetric, we can factor to reveal more copies of the W tensors. The two terms we end up with are identical, so we end up with this final and much simplified result for W. Now on to the next thing on the list, which is X1. Inserting the value of W3 expressed in terms of the new vector fields gets us here. We can then refactor such that the field tensors show up. We're therefore left with this final result. Next on the list is X2. Inserting the values of W1 and W2 expressed in terms of the new vector fields gives us this. Multiplying this out gets us here. The highlighted terms cancel, giving us this. We can then simplify by combining like terms to get our final result for x2. With x1 and x2 done, we can compute x, which is just those two quantities contracted with each other. The only simplification step that's required to get the final answer for this one is based on the fact that f mu nu and z mu nu are antisymmetric. Specifically, this allows us to combine the w terms. Now on to the y's. First we have y1. Inserting the value of w1 expressed in terms of the new vector fields gives us this. Rearranging terms reveals the presence of the w field tensors. Inserting them gives us this result for y1. Now for y2, inserting the values of w2 and w3 expressed in terms of the new vector fields directly produces the final result. There isn't really any opportunity for simplification here. Next we have y3. Inserting the value of w1 expressed in terms of the new vector fields gets us here. This one can also be rearranged to reveal the presence of the w field tensors. The final answer therefore is this. And finally we get to y4. Inserting the values of w1 and w3 expressed in terms of the new vector fields gives us this final answer directly, just like with y2. Now that we have all the pieces, we can compute y. Initially we get this mess. Factoring this partly gets us here. We can then reverse the indices on the w plus mu nu and w minus mu nu tensors in the highlighted factors using the fact that they're antisymmetric. This renders the first two terms in the big parentheses duplicates of the last two. We can therefore combine like terms, producing this. Multiplying the remaining terms out gets us here. We then see that the highlighted terms cancel, giving us this. With y done, we can start calculating the terms required for the evaluation of z. This is especially easy because we've already written out the basic components. Let's start with y2 contracted with itself. Inserting the pieces initially gives us this. The only progress we can really make with this right now is to refactor it and simplify some, which gets us here. The next term in z is y4 squared. Again, we get kind of a mess when we insert the components, and similar to before, refactoring and simplifying a little gets us straight to the final answer. And now for the final term in z, it's x2 squared, and it's even simpler. And just like with the other two terms, all we can really do with it at this stage is refactor it and simplify a little bit, ultimately resulting in this answer. And at this point, we're almost done. All we have to do now is sum the last three results to get z. Initially, upon inserting the different pieces, we get this giant mess. It turns out that the first step to simplifying it is to factor out the squared w terms, which produces this. This factoring is especially useful because the new factor it results in, the highlighted bit, happens to simplify down considerably. Substituting this in gets us here. Next, we need to complete some squares. Adding and subtracting these two terms and rearranging yields this. If you look carefully, you can see that the highlighted terms actually form perfect squares. Writing them as squares leaves us with this result. Next, it's useful to manipulate the blue highlighted terms. First, I addressed them independently, and then I manipulated the difference, which is the actual goal. Inserting this back into z gives us this. You can now see the point of manipulating those blue terms. The yellow highlighted terms form another perfect square. Writing it as a square gives us this final result for z. Now, inserting all the results we've calculated back into the breakdown table we started with leaves us with this. And with this completed breakdown table, we have all we need to write out the spontaneously broken gauge Lagrangian density. Inserting all the pieces gives us this impressive result, where LWWV and LWWVV are the standard names for those parts of the spontaneously broken Lagrangian density. With the spontaneously broken gauge Lagrangian density calculated, we finally have all we need to write out the entire spontaneously broken single-generation lepton quantum electroweak Lagrangian density all in one place. To make the different components clearer and obtain the canonical result, it's necessary to reorder some of the terms and make a few new definitions, ultimately getting us to this final result. We can see many familiar things from particle physics in this Lagrangian. To begin with, there's a massive neutral Z boson and charged massive W bosons, all described by the familiar Proca-Lagrangian for a massive vector field. In fact, it was important that we notice the appearance of the W and Z analogs of the EM field tensors, specifically so that we'd be able to identify the Proca-Lagrangian density here. Also, notice that we have 3 massive vector bosons and 1 massless one as predicted at the beginning. This confirms the remainder of our Goldstone's theorem predictions. Beyond this, we also see a massless left-handed neutrino and a massive electron. In addition, we can see that standard electromagnetism has come out of the spontaneous symmetry breaking of weak isospin and weak hypercharge as expected. And beyond all of this, we of course also see the famous Higgs boson as it manifests at low energy. And with that, we're done. I hope you enjoyed this video, or at least found it interesting. If you did, please consider sharing it with a friend, giving it a thumbs up, and subscribing.